So, let us oh sorry. So, so we were discussing the Condorcet criterion and the plurality method last time when we ended the lecture. A social choice function. So, who is a Condorcet candidate? Let us remind ourselves. A Condorcet candidate or a Condorcet winner is a candidate who beats every other candidate in a head-to-head matchup, okay, by simple majority. And a social choice function satisfies the Condorcet criterion if whenever a profile has a Condorcet candidate. So, a profile need not have a profile of voting preferences need not have a Condorcet candidate always, but if whenever a profile has a Condorcet candidate, the social choice function, if it satisfies the Condorcet criterion, that is, if the social choice function selects the Condorcet candidate as the unique winner, then the social choice function is said to satisfy the Condorcet criterion. So, the point is that Condorcet winner does not always exist, but a social choice function is said to satisfy the Condorcet criterion if it always selects the Condorcet winner if one exists. So, if there is no Condorcet winner, nothing to do, we have to do something else, but if the Condorcet candidate or the Condorcet winner exists, then our social choice function picks out that candidate as the unique winner. And this is and this kind of social choice function is called the Condorcet, is said to satisfy the Condorcet criterion, and we saw that the plurality method satisfies the Condorcet criterion. So, one can define anonymity, neutrality and monotonicity in the setting of 3 or more candidates on similar lines to 2 candidates, and plurality satisfies all these natural properties which we can expect out of a social choice function. But the main problem is that the main problem with plurality is that the plurality voting method does not satisfy the Condorcet criterion. That is, in other words, the Condorcet winner might not be the ultimate winner by the plurality voting method. Okay. There can be other concerns. For example, winner in the plurality method may receive less than 50% of the votes, and it's a winner takes all. So, there is a possibility that a sizable portion of the electorate gets no representation. Okay. So, these are usual problems with the plurality method, although it is very popular for elections. So, in comes another method called Bode account. So, this was developed by Jean-Charles de Borda, who lived in the 18th century, and the Bode account method proceeds in the following way. So, in a preference profile, we give 1 point to the first preference, 2 points to the second preference, 3 points to the third preference, and so on. So, of course, candidates who are consistently placed high in their list of preferences will get low points in this method, right, because you are giving 1 to the first preference, 1 point to the first preference, 2 points to the second preference, and so on. So, low points, roughly speaking, corresponds to consistently high positions in most preference lists. So, what we do is that then we add up the scores of each candidate for all the votes cast, and then the candidate with the lowest total score wins. So, for each preference profile, what you do is that you award 1 to the first candidate who is at the top of the list, 2 points to the candidate who is in the second place, 3 points to the candidate who is in the third place, and so on. and then what you do is that you add up the total number of points received by a particular candidate when you take into consideration all the preference profiles. So in some preference profiles he will be at the top, so he will get 1. In some other profile he will be in the second position, so he will get 2 points, and in some other profile he might get 4 points, and so on. So the one, and then you add up the scores of each candidates for all the votes or all the preference profiles, and the candidate with the lowest total score wins. This is consistent with the intuition that a low score corresponds to consistently high positions in most preference lists, right? So equivalently, one can assign n points to the first preference, n minus points to the second preference, and so on. The one with the highest total wins. So you can just flip the order of the, you can give high points to people placed at the top of the list, and then you have to declare as the winner the person who gets the highest total number of points. So it's these two are equivalent points of view. So believe it or not, the board account is actually used for elections. So it is used for elections in Slovenia and Iceland, 2 nice countries, and it is also used for sports awards, for example, Major League Baseball MVP, etc. So here is an example of board account. There are 4 candidates, and these are various possible preference lists, and for each preference list you have the total number of votes polled. So for example, let's look at candidate A. Candidate A is ranked 2 here, so candidate A gets 2 points here. He is ranked 2 here, so he gets 2 points from here. He is ranked 3 here, so 3 points from here. Ranked 3 here, so also 3 points from here. Ranked 1 here, so 1 point from here. So the total score of A is 2 times 2 from this list, because there are 2 votes corresponding to this list. So 2 times 2 plus 2 times 2 from this list plus 3 times 1 from the third list plus 3 times 1 from the 4th list, and then 1. So this is 4 plus 4, 8, 11, 14, 15. So the Borda score for A is 15. Similarly, you can compute the Borda score for B, C, and D, and you will find that the Borda score of A is the least. So A is the winner under Borda count. Okay. So what are the problems with the Borda count? So you can look at this preference profile for this voting profile for for an election involving 5 candidates, and these are the votes corresponding to these various preferential lists of the candidates. And one can check that the Borda count totals for candidates A, B, C, D, and E are 51, 46, 69, 72, and 62 respectively. So Borda count for candidate B is 46, so that's the least, so he should win by the Borda count method. But 75% of the voters prefer candidate A to B. So if you do a head-to-head matchup between candidates A and B, it is only in this list that B is beating A, otherwise in every other list A is beating B. So if you do the math, 75% of the total number of voters will end up preferring candidate A to candidate B. However, by the method of Borda count, candidate B is winning the election. So here is another problem with the Borda count method. So here is another voting profile for an election involving 3 candidates A, B, and C. The Borda score of A is 9, B is 10, C is 11. So the winner should be A. Now suppose 2 voters in the last column change their votes. So what they do is that they switch their preference between B and C. Okay, the 2 voters in this column, they change their preference to B and C. So now the score of A is 9, but the score of B is 8. So B is the winner. So 2 voters, so they are not doing anything about A. they are just switching their preferential order of B and C, the last two voters, and that changes the outcome of the board account. So the point is that A can cry foul because basically A can say that basically the voters, certain voters are adjusting their relative preference among the two losing candidates, so that morally should not affect A's qualification as a winner, but under board account method it actually changes the scores such that A changes from the status of A changes from winner to loser. Okay. So this is another problem of board account, which brings us to the property of independence of irrelevant alternatives. So the above example shows that board account can violate the so-called independence of irrelevant alternatives, or IIA, this property. So if A is the winner of an election, then it is, so what does independence of irrelevant alternatives, or IIA, stand for? So IIA stands for the following: if A is the winner of an election, then it is not possible for B to become a winner without some voters changing their preference, their relative preference from A to B. Okay? So the point is that if A has won the election by some method, then the method should be robust enough so that the status of A as a winner cannot be changed unless some voters switch their votes from A to B. So in their preferential order, they should switch, they should change the relative order of A and B. Okay? So unless really, so basically morally this is saying that unless some voters stop preferring A to B and instead start preferring B to A, the status of A as a winner should not change. So this property is called IIA, or independence of irrelevant alternatives. What does irrelevant alternative stand for? Irrelevant alternative stands for the losing candidates. So in the previous example, in the previous slides, these are the losing candidates B and C. So these are the irrelevant alternatives because they have lost the election, and what the voters were doing was that there were certain voters who were sort of changing their relative preferential order of the irrelevant alternatives, and suddenly the status of A as a winner was being switched to that of a loser. What IIA is telling you is that a good voting method or a good social choice function should have the property that the irrelevant alternatives should be, so that the final outcome of the elections should be independent of the irrelevant alternatives. So the irrelevant alternatives and their relative order should not matter in the determination of the final outcome, should not affect the final outcome. Okay? So that is irrelevance of independence of irrelevance or irrelevant alternatives. So put in another way, if the system ranks A above B in the presence of C, it should still rank A above B when C is not there. Okay? So that's another way of putting it. So here C is the irrelevant alternative, and if the system ranks A above B in the presence of C, then the presence of C should not matter morally. So even if C is not present, A should be better than B. Okay? So in some sense, this is asking for some consistency that okay, so you have some method of finding the relative scores for various candidates and declare the winner by virtue of that. But if you look at every pair of candidates, then your final outcome should be consistent. Okay, it should be consistent down to the level of every pair of candidates, or at least the winning candidate. So we would like our voting system to be insensitive to the presence of such irrelevant alternatives. So plurality is not independent, does not satisfy independence of irrelevant alternatives. So here is a voting profile involving 3 candidates, A, B, and C. Plurality method tells you that A is the unique winner with 49% of the first place votes. However, if the voters who ranked candidate B first instead ranked candidate C first, so for example, those who ranked candidate B instead, those who ranked candidate B here first, instead if they switch B and C, for instance, C could win and A could lose, even though no one has changed their preference of A over C or C over A. Okay. So, no votes in the relative preferential order pairwise head to head matchup of A and C, nothing is being changed. What is being changed is the relative order of B and C, but still the final outcome of the winner is being changed. Okay. So, and A is losing and C becomes the winner. Okay. So, this is this example tells you that plurality is not IIA. So, it turns out that it is a pretty tricky condition to meet, because plurality, which is one of the most natural voting methods when there are multiple candidates, more than 2 candidates, does not satisfy IIA. So, here is another method, it is called sequential pairwise voting or SPV. So, the idea comes from sports tournament. So, a team keeps playing in the tournament as long as it keeps winning individual contests, and as soon as it loses one, it is eliminated forever. So, in some sense it is like the knockout phases of a tournament, right. So, the team that wins the final contest is the tournament winner. So, in voting theory, the schedule of head to head matchups is called the agenda. So, in some sense you can think of it as the sort of a lineup of matches in a tournament, right? Like in World Cup football or World Cup soccer, you know, it's very important as to who is playing against whom, right? That's very important. So, in voting theory, the analog is the schedule of head to head matchups, and it's called the agenda. Usually a sequential list of candidates, and the matchups, usually it involves a sequential list of candidates, and the matchups follow the order of the list. So, for example, if the candidates are listed as A, B, C, D, E and so on, then first A plays against B, then the winner of that plays against C, then the winner of that plays against D and so on. Okay. So, this is called sequential pairwise voting, or SPV for short, or the agenda method. So, suppose we have a number of candidates A, B, C, D, etc. We first pit A against B and ask who the voters prefer using majority rule. Then we pit the winner of A versus B against C, and then the winner of that contests against D and so on. So, the final winner is the last one still standing. Okay. So, this is how it works. So, remember, if there is a Condorcet winner, then she will certainly be a winner under SPV, because the Condorcet winner beats every other candidate in a head to head matchup. So, the Condorcet winner will definitely, wherever you place the Condorcet winner in the list, and whoever precedes him in the list, doesn't matter, because the Condorcet winner, when he comes to contest, Condorcet winner is going to, so every contest, every actual contest or comparison in this method is a pairwise or a head to head comparison, and the Condorcet winner is the candidate who beats every other candidate in a head to head matchup. And since in sequential pairwise voting, every actual contest, like here or here or here, every actual contest is just a pairwise contest using majority rule. Therefore, the Condorcet winner is going to come up on top in any SPV method election. Is that clear? Any questions? So, here is an example of SPV. Here is a sequential. Here is a voting profile, and suppose you have the agenda A, B, C, D. So, you list the sequentially list the candidates as A, B, C, and D. Then you can calculate the pairwise head to head matchups between the candidates from these preferential profiles or voting profiles, and you will find that A beats B. So, A is the winner of this. Then you compare contest between A and C. Again, from the voting profiles, you figure out that A beats C. So, A is the winner here again, and you compare between A and D, head to head matchup, D beats A. So, D is the winner. Now, let us try with a different agenda, B, D, C, A, and you will find that B, so first B will contest against D, so B will beat D. So, already the winner of the previous list has already lost. So, as you can already see that there is something going on here. So, B has already beaten, excuse me. Excuse me, yeah. B has already beaten D, then C will beat B, then A will contest against C, and C will beat A, so A is the winner. So, by changing the schedule, you can change the winner. So, this is one of the main problems with SPV. If SPV is applied to a sequence of agendas A, B, C, D, then D is the winner, but if it is applied to a different schedule, then someone else is the winner. So, of course, this is troubling, and this leads to the famous Pareto condition in voting theory, also known as unanimity. So, it was found, it was discovered by Wilfredo Pareto, who worked in the 19th and 20th centuries. So, the above example shows that SPV can violate the following condition. If every voter ranks B over D, then the system should rank B over D. Okay? In particular, if every voter prefers B over D, then D should not be the winner of the election. Okay? So, notice here that every voter is preferring, in every preferential list which has gotten any votes, B is above D. So, there is no question, each and every voter prefers B over D if you just compare between B and D. However, in SPV violates the condition that if every voter prefers B over D, then D should not be the winner of the election, because D, as we saw, could be the winner of the election. Okay? So this is a problem with the SPV. So basically, it violates the Pareto condition or unanimity, which says that if every voter prefers one candidate over the other, then the other candidate, who is the less preferred by every voter, should not become the winner of the election. It makes no sense, right? Because for this particular candidate D, there is at least one candidate who is preferred to D by each and every single voter. So there is no logic that D should be the winner of the election. So this sounds like a natural condition. This is called unanimity or the Pareto condition, and you would agree that Pareto condition is very reasonable. So examples of Pareto conditions. So dictatorships are satisfy the Pareto condition. So if what is the reason? If candidate X is ranked above candidate Y in every profile, then what is the dictatorship method? There is one particular important voter called the dictator, and whatever he chooses is the final preferential list, and the winner he chooses is the winner of the election. Now, if now if candidate X is ranked above candidate Y in the preference list of every voter, then in particular for the dictator voter, also candidate X will be ranked above candidate Y. Therefore, Y cannot be the winner, because the winner will then be just the person who is at the top of the list of the chosen by the dictator, right? So dictatorships satisfy the Pareto condition. Monarchies are not Pareto, because monarchy method, you remember that is a method where there is one candidate who is a monarch, and no matter how the votes are cast, this candidate is declared the winner. So of course, the monarch might be at the bottom of every voter's preference list, but he will still be the winner, right? So monarchy clearly doesn't satisfy the Pareto condition. So here is another method. This is the Hare system, or the instant runoff voting. This was developed by Sir Thomas Hare, who lived and worked in the 19th century. So what we do in the Hare's method is that we examine the voter's first preference and eliminate the candidates who have the lowest number of first position. Okay? Having eliminated these, we examine the new preference lists and repeat the above procedure. And the winner is the last one who remains. I mean, tie is possible, but let's omit it for now. So example of Hare method. So here is a voting profile with 4 candidates, A, B, C, and D. So A and B receive only one first preference, first place vote. So whereas C and D receive 3 and 2 first place votes respectively. So A and B are eliminated after round 1. So A is gone, so you just remove A and B. A is gone and B is gone. You remove A and B from each list. So now what you do is that now you have two candidates, and you can, if you like, you can merge the lists for the two candidates. So this list is just CD. This list is also CD. So for the list CD, you have 2 plus 1, which is 3 votes. So this list is DC. This list is also DC. So you also have 2 plus 1, which is 3 votes for DC. Sorry. This list is also DC. So you have one more. So you have 4 votes for DC. So now C and D are left, and you just combine the preferential voting lists in this manner, natural manner. C now has 3 first place votes. D has 4 first place votes. So D is the winner. Okay. So this is, so you just go by eliminating the worst performing candidate in terms of the first place. Okay. One by one. So remarks on the Hayes system. So while we described Hayes method as consisting of rounds, the original profile contains all the information needed to compute the winners. So this can be done instantly by a computer. So although in principle you are doing one round after another, I mean, it's like the entire information needed to do it is actually contained in the full original voting profile. So you can just feed it into your computer and write a program, and it will do it for you in a jiffy. Okay, so computationally finding out is not the winner is not that big a deal. So this form of runoff election assumes that voters hold consistent preferences once candidates are removed from considerations. Unlike in runoff elections where voters must return to the polls after each round. So there are, so there are runoff elections. So in the previous example of A, B, C, and D, there were 4 candidates to begin with in the first round. A and B were eliminated, and then there was a runoff second round with just C and D. But in the Hayes method, what we did was that we did not hold another election with just C and D. Instead, what we did was that we just combined the voting profiles which was already present and calculated the amalgamated voting profile for just 2 candidates C and D, right? So this is so there are many real elections in which this does not happen. For example, if you look at presidential elections in France, what happens is that there is first round of there are many candidates, and then there is a runoff election between the top 2 candidates, who is and then the voters are supposed to go back to the polls and cast their votes, right? So that kind of runoff, which is also popular in practical elections, is not the Hayes method. So in Hayes method, voters do not get to vote again in the runoff. You just vote once, give the full preference lists, and in the subsequent rounds, you just compute using the original preference list by repeatedly amalgamating them. So, and the drawback of Hayes method is actually exactly that. So, if certain candidates are removed from the preference list, then Hayes method assumes that the voters would still hold the same relative preference between the two final candidates, right? So this might not happen. So that's why in practical elections, it's often the case that the voters are asked to come back again and vote afresh for the runoff election. So this is a problem of the Hayes method, but it still has its own uses. So for example, it is used to elect members of the Australian House of Representatives. It is used to elect President of India by Parliament and state legislatures. Okay. So although I am from India, I did not know this fact. So I learnt it while teaching this course. Okay. So here is some more on the problem with the Hayes method. So here is a voting profile with 3 candidates, A, B, and C. So B and C have 4 first place votes, whereas A has 5. So B and C are eliminated. So if you see, B has 4 first place votes, C has 4, whereas A has 5. So B and C are eliminated, leaving A as winner. Okay, plain and simple application of Hayes method. So suppose now that the voter in the last column switches the position of A and B. Okay, so suppose the voters in the last column switches the position of A and B. So that should work in favor of A, right? Because A was winning before and now someone has switched his preference to A. So definitely A might be actually winning more. So let's see what happens. And let's now apply Hayes method to the altered profile. So A and B switched here. So this profile becomes ABC. So ABC has 6 now. And CBA and BCA are 4 and 3 as before. So, so now in round 1, B is eliminated because B has the least number of first place votes. Now, if B is eliminated, let's eliminate B from everywhere. So now A has 6 first place votes, whereas in both of these profiles, C is above A. So these are both in favor of C. So if you combine the amalgamate or combine the voting profile after eliminating B, AC would just remain at C from this profile, whereas both of these two profiles would contribute to C first and A second. So you would get total of 7 here. So now C becomes winner. So by making a switch of preferential order of candidates by some voters, which should be advantageous to A, actually the Hayes method makes turns A from winner to loser. So of course that is not good for a voting method, so that's a drawback of the Hayes method. Okay. So this example shows that Hayes system can violate the following property. If A is the winner of an election, but now some voters change their ordering to move A higher on their individual preference lists, like these voters, this guy, this particular voter, then A should still be the winner in this new scenario. So very logical, natural concept. So this is called the concept of monotonicity, and which we have seen for earlier for 2 candidates. Okay. So so this is the multi-candidate version of monotonicity. So the basic question is there a perfect or a best voting system? So far we have seen many different voting systems, the plurality method, Borda method, SPV method, Hayes method, and we are talking for about 3 or more candidates. So we have seen many voting methods, 4 different ones. Each of them seems reasonable but may violate some of the following desirable properties. So Condorcet winner criterion, independence of irrelevant alternative or IIA, Pareto condition, monotonicity. So these are some conditions that we have studied last lecture and today's lecture. And many of these natural voting methods might actually violate some of these criterions. Okay? So we have not yet found one which satisfies all of them. So the question therefore boils down to, is there a voting system which satisfies some basic properties like anonymous, so all voters must be equal, so all votes must be equal, and neutral, so all candidates should be equal. So anonymous means it should not be, for example, it should not be like a dictator. And neutral means all candidates are equal, so for example, it should not be like a monarchy, so it should be something real. And always produces a winner, decisive, and satisfy these natural properties. And the answer given by the famous scientist Kenneth Arrow is no. So Kenneth Arrow just died a couple of years ago. He is a famous scientist from the 20th century, and the discovery of the impossibility theorem, named after him, named after Arrow, was one of the main reasons that Kenneth Arrow was awarded the Nobel Prize in Economics. So Arrow's theorem, which he proved in 1950, was the following, says the following: with 3 or more candidates, the only voting system which satisfies Pareto, IIA, monotonicity, and decisive is a dictatorship. So we wanted anonymous, neutral, decisive, and these 4 conditions: monotonicity, Pareto, independent, IIA, and Condorcet. And Arrow says that if you have Pareto, which we want here, if you have IIA, which we want here, and if you have monotonicity and decisive. So, monotonicity we have here and decisive. Then the only function which works is going to be the dictatorship, but the dictatorship is of course not anonymous, so there is no perfect voting method. So, the question is there a voting system which is anonymous, that is all voters are equal, neutral, all candidates are equal, always produces a winner, that is decisive, and satisfy Condorcet winner, Condorcet criterion, IIA, Pareto condition and monotonicity, and the answer is a big no by Arrow's theorem, and it was a really big no because it led Kenneth Arrow to the Nobel Prize in Economics. Okay? So, with this we complete the lectures, and from now on we will move into overview and review. Okay? But first 5-minute break. Okay, so let us begin with overview and review. So basically, in the beginning, we will discuss or recall some concepts which probably most of you know from beforehand, from before taking this module, but I just want to sort of refresh your memories about these concepts, because this might be helpful in understanding some of the topics that we have been discussing in this module. Okay, so one of the basic objects that we have been talking about directly or indirectly is are sets. So what is a set? A set is a collection of objects, each of which is called an element or a member of the set. So a set is a primitive concept in mathematics, and there is no real rigorous definition of what it is. So for example, you can think of, if I buy some oranges from the market, if I buy 9 oranges, so you can think of it as a set of 9 oranges, or 3 apples and 5 oranges. Okay, so of the set of all real numbers between 0 and 1, the set of all positive integers between 1 and 10, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, it is as basic as that. And we write, so this symbol just denotes x, this element x is in the set A. Okay. So that's just the meaning of this symbol, and we write that x doesn't, this symbol with a cross, if x is not a member of A. So, the goal is to let the reader know which elements are in the set and which are not. When a set is small, we can fully list all its elements between curly brackets. So for example, 100, For example, 101, 103, 107 and 109, notice that 105 is missing. So it's not just the odd numbers between 100 and 110. So these are just is the set of all primes between 100 and 110. Notice that 105 is missing. So it's not the set of all odd numbers between 100 and 110. Instead, it's the set of all primes between 100 and 110. We give it a name, say B, and write B is equal to, the set B equal to 101, 103, 107 and 109. We can also list sufficient elements to show the pattern. For example, we can consider the set of all natural numbers, which are all the positive integers, and it is usually denoted by the script n, and this is just 1, 2, 3, 4, 5, 6, etc. So containment of sets. So the set A is a subset of the set B if and only if every element is of A is an element of B. So this notation means if and only if. So any element that belongs to A should also belong to B. So for example, here, if you look at the set of all primes between 100 and 110, this is a subset of the set of all odd numbers between 100 and 110, right? So you have an extra element there, which is 105. So this is the notation. So this denotes A, the set A is contained in the set B, or we say that the set B contains the set A. And in principle, A could also be the same as B. So that's why it's like a less than equal to sign in some sense. So there is this horizontal sign, which means that A could, which includes the possibility that A could also be the same as B. So if both if A contains B and B contains A, if both are true, then of course A has to be the same as B. So this is just some notation. And A is a proper subset of B if it is in the previous example. So the set of all primes between 100 and 110 are a proper subset of the set of all odd numbers between 100 and 110, because the set of all odd numbers between 100 and 110 contains one extra element. So it's not the same as the set of all primes, but it contains one extra element. So A is a proper subset of B if B contains more elements. And it is so in that case, A is a subset of B and A is not equal to B. And you can do analogous symbols, like you can have the containment symbol with a cross, which means not contained in, and so on. And the proper subset notation is A is contained in B without the equality sign. Okay, so it means proper containment. So, he is a proper subset. So, B contains extra elements which are not in A. So, notice that contained in involves a relationship between two sets. So, one set is smaller than the other, belongs to, that is the epsilon symbol in the previous slide, denotes relationship between an element and a set. So, these two are not the same. Now, let us look at some basic set operations. So, you can always think of sets by drawing blobs like this. Okay? So, suppose A and B are two sets, and we will come to a more formal study of that in a moment. So, if A and B are two sets, then the intersection, so think of these are containing elements of the two sets. So, A intersection B are the elements which are contained in both the sets A and B. And the union is the set of all elements that is either in A or in B. Okay? So, these are the notations. So, A cup B is A union B. So, it contains all the elements which are either in A or in B, or A cap B is the intersection of A and B. So, elements which are both in A and in B. Okay? So, these pictures brings us to the study examples of what are called Venn diagrams. So, it is natural to study sets like this. So, if A and B are two sets, then the union is the shaded region in green, the intersection is the shaded region in red. Okay? So, elements which are either in A or in B, so everything combined in A and B, so green. A intersection B is both in A and in B, so it is much smaller. So, it is the intersection of the two disks A and B. So, it is a shaded area in red. Complement. So, suppose you are there is a natural universal set inside which you are working. So, suppose you are always working within the set of integers. So, that's you are always talking about integers. So, integers is your universal set, and then you can think of the set of even numbers and the set of odd numbers. So, of course, integers consist of even and odd numbers. So, odd numbers are precisely those that are not even. So, therefore, so that brings us to the notion of complement, that example. So, the complement of A is just the elements which are not contained in A, but are contained in the universal set. So, the complement of A are the elements which are contained in the universe of things which we are studying, which are members of the universal set, but which are not in the set A. So, for example, if you are studying integers, then of course your universe or your universal set is just the set of all integers, and it consists of odd and even numbers. So, if you just look at the set of even numbers, then the complement are precisely those integers which are odd, right, which are not even, that is odd. So, the set of odd numbers is the complement of the set of even numbers within the universe of integers. So, here are some basic notions of counting regarding sets. So, the size of the set A denoted by modulus of A is the number of distinct elements in A. If the number of distinct elements in the set is not finite, then we say that the set is infinite. So, for example, the set of all integers between 1 and 10 is of course a finite set. It has 10 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The set of all integers is an infinite set, because the number of elements in the set of integers is not finite, right. So, whatever number you choose, you have more elements in the set of integers than that cutoff. So, whatever cutoff you choose, the set of all integers has more elements than that cutoff. So, this is one way to specify that the set of integers, the set of all integers is an infinite set, because the number of elements in the set of all integers is not finite. So, if A and B are disjoint, so again think of in terms of Venn diagram. So, if A and B are disjoint, then the total number of A is the total number of elements in A union B is exactly the total shaded area. So, of course, this is the area of A plus the area of B, right. So, there is no double counting. So, there is no overlap. So, there is no double counting. As soon as there is overlap, there is double counting. So, you have to take care of that. So, if there is overlap, you have to be a little careful. So, A union B is the sum of the two areas. So, cardinal size of A plus size of B, but you have double counted the overlap area twice. So, what you do is that you subtract of the area of the overlap, which is exactly the cardinality of the intersection, which is exactly the size of the intersection. Okay? Any questions? Similarly, you can do this for, so this is the famous inclusion and exclusion principle or INEX principle. For two sets, here it is in action for three sets, you can do it for any number of sets actually. So for three sets it's more complicated because you can have different kinds of overlaps, overlap between pairs of sets, overlap between all the three sets and so on. And the INEX principle, you always follow what you always stick to is that the cardinality of the set in the Venn diagram is actually the area of the circle representing that set in the Venn diagram. Okay, and then you just adjust these intersections, adjust these areas so that it adjusts the overlaps or adjust the areas of the overlaps so that it gives you the total area of the three circles taken together. Okay. So notice that for the single circles it is positive, for pairwise overlaps it is negative, but then again you have to adjust back for three-way overlap by a positive amount. Okay. Any questions? Okay. So let's now look a bit at functions. So what is a function? So of course we know what are functions, right? But anyway, what is a function? A function is basically you have two sets A and B. So think of your favorite function. So for example, maybe you are working on the interval 0 to 1 and your favorite function is 1 minus x, fx equal to 1 minus x. So it just switches, right? It just flips the interval. So f0 is 1, f1 is 0, f half is half. So exactly you were going from 0 to 1 in the interval, and fx equal to 1 minus x basically makes you go from 1 to 0, right? So you can do any kind of functions, and most generally a function is just you feed in some argument and it gives you a value, right? That's what a function is. So it associates to each argument in A and exactly a particular element in B. So the only property it has to satisfy is that for every argument it has to have a single value. It cannot say that fx equal to 1 or 2 or 3 or something like that, right? It has to have a specific value for every input x. So if f associates B to A, then we write B is equal to f of A and say that B is the image of f under A. The set of inputs is called the domain, and B the place where the outputs lie, that's called the codomain, and the set of all possible values of the function is called the range. So just some terminology. Any questions? Okay, so these were some sort of general definitions about sets and functions. So not directly for problems per se, but just to understand and clarify some concepts that we have been discussing in the lectures and in the questions and so on. Okay, just to have a baseline for so that there are no unclear concepts. So let's now get into the main things. So we start again our review from personal finance and interests. So compound interests. So all interests for us are compound interest. So if you invest $C0 with an annual compound interest of alpha, you will have Cn dollars at the end of n years, which is where Cn is related to C0 as 1 plus alpha to the power of n times C0. So this is exponential growth, so to say, right? We will again come to it. So alpha is often written in percentage, so 5%, but for applying this formula, of course, you have to convert it to a fraction, which is 0.05. So there are 4 parameters in this proposition: C0, alpha, n, and Cn. The typical questions are to find the 4th one, assuming we know the other 3. So this is the way most of the questions work. So, just a bit about linear and exponential growth. So, the different growth of investment after under simple interest and compound interest is exactly the comparison between linear and exponential growth. So, if it is simple interest, then you get you get a linear growth in time, because essentially you get the same percentage of interest, you get the same amount of interest every year, and then the sum after t years is a plus bt, so it is linear growth in t. Compound interest is exactly exponential growth, ft equal to a times c to the power of t, which is exactly of this form. So, just replace n by t, okay. And exponential growth is much faster than linear growth for c bigger than 1, okay, c bigger than 1. So, you can also do semi-annual, quarterly and other rates. So, sometimes interest rates are presented on a monthly or a quarterly or a semi-annual basis. So, here is an example. If you have a loan amount C with an interest rate of 2% compounded quarterly, how much do you owe after 1 year? So, if you were doing linearly, it would be 4 times, so for every quarter you have 2%, so you just add them up, 8% for the year. So, if you 8% is interest and of course the principal is C, then it's 1.08 times C. But this is the wrong answer because interest rate is compound. So, exactly you do the same thing, n units of time and alpha is 0.02, n equal to 4 units because there are 4 quarters in a year. And you get 1.02 to the power of 4 times C, where C is your starting capital, which is 1.0824 times C. So, it's actually more than 1.08. So, it will be more. Any questions? Okay. So, conclusion is that such a loan has annual interest rate of 8.24% rather than 8%, and the rate 8.24% is often called the annual percentage rate or APR of the loan. Okay. From yearly to monthly rates. So, if you know the yearly rate is alpha, how do you calculate the monthly rate? So, if a loan has an annual interest rate of I, what is the monthly rate alpha? So, alpha and I are related again in the following manner. So, 1 plus alpha to the power of 12 is I, because is 1 plus I, because I is the yearly interest rate. So, if you start with C0 amount of money in the beginning, at the end of the year you get 1 plus I times C0, and if you get 1 plus I times C0 dollars, if you start with C0 dollars and the monthly interest rate is alpha, then you have 12 units of time in the monthly count. So, you have 12 months in a year. So, 1 plus alpha gets multiplied 12 times or raised to the power 12 times, and times C0. So, that is your total amount what you get, and the month, and these two amounts must be equal because they are just two different expressions for the amount of money you get at the end of 12 months. So, this times C0 should be equal to that times C0, C0 cancel. So, you get the equation, the equality of 1 plus alpha to the 12 equal to 1 plus I. In other words, 1 plus alpha is 1 plus I to the 1 over 12. Okay. So, this is how you go about calculating. Future value and present value, what is having X? So, if you having X in K dollars, having X dollars in K years time. So, if you have X dollars in K years time, what is it worth today, assuming the rate of investment returns is I. So, you want to, so you know that the rate of investment returns is I and per annum, and you want to have X dollars back after K years. So, how much should you invest today? What is the present value? So, that is the question. So, in terms of the proposition, we want to find C0 assuming that we know alpha n and Cn. Solution is that after K years, if you invest Y dollars today, after K years, it will go to 1 plus, grow to 1 plus I to the K times Y, where I is the annual interest rate. So, if you want this to be, you want to get X dollars after back after K years, then this amount should be X. So, you have this equation. So, you can solve for Y is equal to X over 1 plus I to the K. Okay. This amount Y is called the present value of X in K years time. So, here is a mortgage problem. let us consider a rather complicated problem in terms of mortgage. If you borrowed $100,000 at 6% annual interest rate, we paid monthly over 25 years. Now, how much is your monthly payment and how much do you owe after 15 years? So, what makes this problem complicated? The thing that makes this problem complicated is that you are paying back monthly, right? Now, as soon as you pay your first monthly installment, the amount you owe to the bank has actually reduced. So, you should not be paying at the 6% annual interest rate for the next for the whole amount for the next month, but you should pay for a reduced amount which takes into account the fact that you have already returned some of the money to the bank. So, that is the sort of the crux of the problem. That is why this problem is slightly complicated. So, what you do is that more generally, suppose you borrowed $C at annual interest rate I, paid monthly over n years, how much is your monthly payment R? So, this is problem 2 as stated here is just a special case of this with particular values of C, I and N, and our goal is to figure out R. The solution is again we went over this in details in the lecture, but today let us just recapitulate it. The solution is R equal to 1 plus alpha to the 12n times alpha times C divided by 1 plus alpha to the 12n minus 1. So, what is alpha? So I is the yearly interest rate, annual interest rate, alpha is the monthly interest rate. So, but the monthly interest rate alpha and the yearly interest rate I is related by this equation. So, alpha is the monthly interest rate. So, recalling that the monthly interest rate alpha and the yearly interest rate I is related by this equation 1 plus alpha to the power of 12 equal to 1 plus I, we can simplify this as R equal to C times alpha times 1 plus I to the n divided by 1 plus I to the n minus 1. Okay. And how much do you owe after k months? So, after k months you owe this amount. So, Ck is C times 1 plus alpha to the k. So, C is the initial amount you have invested, you have borrowed, minus R which is the monthly payment times 1 plus alpha to the k minus 1 divided by alpha. Okay. And these follow from considerations which is basically sort of doing carefully the carefully tracking the growth of the compound interest. Here is a retirement example. So, on your retirement you have a lump sum of 200,000 to provide an income until you die. The CPF estimates that you will live for 20 extra years and assumes you can earn 4% after its expenses on the capital you give to it. What amount would you expect to receive each month? So, again this is an example. So, here the roles are reversed because the CPF is giving you back, paying you back money monthly. So, it is as if you have lent money to the CPF and it accrues certain interest and the CPF is paying you back monthly. So, now again you use a similar formula R equal to C times alpha times 1 plus I to the n divided by 1 plus I to the n minus 1. Alpha is the monthly interest rate corresponding to the annual interest rate I, and if you slot in the values given in the problem you get this figure. So, here is another example involving savings plans. So, consider the retirement savings plans of two twins Ann and Beth. Ann saves $A at the beginning of each year for 40 years. Beth starts 20 years later and saves $B for each year for 20 years. So, Ann saves more for double the time what Beth saves. Now, but suppose both of them want to have the same amount of money, same amount of retirement savings, and they retire in 40 years time. So, how much more must Beth save, assuming that their savings grow at the same annual rate 3%. So, basically there are two twins who will retire together at the end of 40 years. and one of the twins Ann saves for the entire period of this time $8 per year. The other twin Beth, she saves only for half the time, 20 years, and she saves a different amount per year, $B. Okay, and they want to have the same amount of money at the point of retirement. So at the point of this saving, and you know, these investments grow at the annual rate of I. So at the point of retirement, they want the same amount of savings. So of course, Beth has to save more per year than A. The question is how much more. And if you can do the math, so if you start with $8, every year it grows by A, but you are also adding $8 per year, so it gets into a sum of a geometric series, which we will again recap in a moment. And after k years, you get that the total sum which your $8 per year investment has grown into is this quantity. Yk is equal to A times 1 plus I times 1 plus I to the k minus 1 divided by I. So this is for A savings at $8 per year, and for k years. So now we will calculate the total savings for Ann and Beth by slotting in two different values A and B, and slotting in two different values of k, which is the number of years, which is 40 for Ann, k equal to 40 for Ann, and k equal to 20 for Beth. So for Ann, you put in the values in this formula and you get A equal to A times 1.03. So 0.03 is the value of I, which is the annual interest rate, and find the corresponding value for Beth. So these two have to be equal, which immediately gives you a value for the ratio B over A, and you can approximately calculate this as roughly equal to 3. So just because Beth is saving for half the total number of years as Ann, in the 20 years instead of 40, she has to save 3 times more money every year. So here are some inequalities involving real numbers, which we also came across during our study of interest rates. So for any integer n bigger than 2, bigger than or equal to 2, and positive real numbers p1, p2, pn, you have the inequality of the various means. So this is the simple average of the arithmetic mean, or AM. This is the another mean, it's called the geometric mean, or GM. And this is the third kind of mean, which is called the harmonic mean, or HM. And the inequality states that for any n bigger than or equal to 2 and positive real numbers p1, p2, pn, the HM is less than or equal to the GM is less than or equal to the AN. Okay? A bit about quadratic equations. So a quadratic polynomial is of the form fx equal to ax squared plus bx plus c, so functions of this form. We can find its roots, that is solutions to fx equal to 0 by this kind of formula. If b square minus 4ac is positive, then of course you are taking the square root of a positive number. So it is well defined and everything. So fx has two real numbers as its solution. Fx equal to 0 has two real numbers as its solution. And b square minus 4ac is 0. Basically this is 0, so there is only one solution, which is b over minus b over 2a. And b square, if b square minus 4ac is less than 0, then this is the square root of a negative number, which is not a real number, so it has no real solution, right? There is no real number which solves this equation. Any questions about this? So let us do a bit of arithmetic and geometric series, and then at that point we will call it a day. So an arithmetic progression is a sequence of numbers where you start from a certain starting number, or the first term called a, and from this first term you keep growing by equal amounts linearly in every step. So a plus d, a plus 2d, a plus 3d, and so on. Each number is obtained from the preceding one by adding a fixed number d called common difference. So for example, 100, 105, 110, 115, 120, and so on is an arithmetic progression. First term is 100, common difference, which is the increment in every step, is 5. And if you take an arithmetic progression and calculate the sum of the members of that arithmetic progression between some bounds, 0, so the first term up to the first n terms of an arithmetic progression, you get this. Actually, this is n plus 1 terms, n plus 1 terms. So it is this, so it will, you can expand it as this kind of a sum. It's called an arithmetic series, and there is a simple formula for an arithmetic series, which is n plus 1 times 2a plus nd over 2, where a is the starting, n is the starting point, where a is the first term, d is the common difference, and n is the length up to which you go. So n plus 1 is the total number of terms. Okay. Similarly, you can have a geometric series. So a sequence of numbers a of the form a times r square, a times r cubed, etc. is called a geometric progression. Each number is obtained from the previous one by multiplying by a fixed number called r, which is called the common ratio. And a is the first term and r is the common ratio. A geometric series is the sum of these sum of the successive first n plus 1 terms in a geometric progression. So let's now look at a formula for the sum of the geometric series, like we did for the arithmetic series. The formula for the geometric series is exactly this. The sum of the geometric series is a times r to the n plus 1 minus 1 over r minus 1. So notice that this is true for r not equal to 1, because if you put r equal to 1, you will have division by 0, which is not possible, which is not allowed. So for r not equal to 1, you have a simple formula for the geometric sum of the geometric series, and in particular, if your geometric series, if the starting number is 1, if the first term is 1 and the common ratio is x, then you get a series of this form, 1 plus x squared up to x to the k minus 1, which you can simplify as 1 minus x to the k over 1 minus x. So this is the point where we would like to stop today, and from the next in the next lecture we will start from linear versus exponential growth. Okay.